So what problem in particular are you trying to solve now using Einstein's principle of locality?
Okay. Now that I have done this with fermions and I'm pretty convinced, and I think it has inspired me in some sense to propose a formulation of how the structure of reality works and how this can be then translated into constructor theory. So what I'm aiming at is that to use the principle of locality, the principle of interoperability that is very present in the constructor theory of information, and the definitions of superinformation media and information media, to basically understand what are all the possible dynamical laws of physics. Like, it's maybe ambitious, but it's also very abstract in the sense that what I want to know is combining these principles, which are the possible systems that adhere to those notions. And what are the differences between those systems? So for example, right now we have classical information and quantum information. And what I want to know with this framework and having the principle of locality is exactly what differentiates these two. This is the first thing that I want to do. That is why interoperability principle and the superinformation media definitions are so important in my future work. But not only know exactly what are so different about them, and not only about talking about as a lot of physicists do, computational ability or this sort of stuff, like rather what is different in the structure, what is different on the capabilities of a theory, what is really inherently different between those two. And then I want to pose the question of whether there are different types of information. So if there is something in between classical and quantum information, or if there is something beyond quantum information.
So could you define the principle of interoperability and maybe tell us what superinformation is, or a superinformation medium?
Sure, excuse me for that.
No problem.
So the principle of interoperability, it's a principle that like as all principles, it just makes sense, okay? Principle of interoperability, it says that if you have a system that can transport information or can be used for information purposes, then the properties of the information cannot rely on what the system is made of exactly. So for example, let me put an example because I don't know if I'm going to explain myself. Let's go back again to the glass of water. If I have a glass in top of the table, I can communicate information to you. I can do it because we can convene that if the glass is set on the table straight, then I will be sending you, this would mean that once you see it, this is a 0. But if I lay it on the table, this would be a 1. So I can communicate information to you. But the principle of interoperability precisely means that what information is this ability to transform this state from being on top and or laying on the table to other types of physical processes that encapsulate the same information. Like for example, you can put it on a transistor, or you can, I don't know, wave your arm up and down. So it's this ability for systems that they need to have in order to communicate this information. And then for superinformation media, basically it's, first I will need to explain what information media is. Information media is just a way to define information within the realm of constructor theory, which is to only talk about what can be done, what cannot be done. So we will say that the system can have information or can transport information, or however you want to interpret it, if it satisfies two properties, if two tasks can be performed. First is that it has a set of attributes that are non-overlapping, so that you can distinguish between, like, if the glass is up or the glass is down. And more importantly, you have to be able to switch between those. So you have to be able to grab the glass and put it on top of the table, or put it laying down on the table. So you have to be able to, how it's called, to permute the different attributes of your system. But not only that, you have to be able to copy them. So this is the connection with the principle of interoperability. You have to be able to have another system, for example, you log in and with your eyes and detect the glass, and be able to get a copy. So like if you see that the glass is on top, then you will write a 0. And if you see that the glass is laying down, you'll write a 1. So you have effectively copied the information from the glass to your paper. And now you have two copies of the same information. So if a system is able to perform those two tasks, then we say that, how it's called, that it's an information media. And a super information media is a type of information media, as the word suggests, that basically it has special properties that resemble a bit quantum behavior, which basically is that you have some type of variable or observables that you cannot measure at the same time one and the other. So this in quantum theory, as it's common in like this type of outreach things, it's explained that quantum physics has this property that you cannot measure at the same time. It's the uncertainty principle. At the same time, for example, how fast the car is going and where it is. So if you can do this for a car, but if you do it for an electron, then you cannot do that. Like either you know exactly how fast the electron was going, or either you know exactly where the electron was. So this super information media, it's an information media that has this sort of flavor property of knowing whether, how it's called, having these two observables that are not compatible between themselves. So with the principle of interoperability, the Einstein's principle of locality, I'm planning to have a framework and to then explain the difference between what a super information media can do, or what is the structure within a super information media, and with a regular classical information media.
So it sounds like you want to take some of these constructor theoretic principles, like the principle of locality, the principle of interoperability, and also the definition of super information media, and you want to show what physical systems could possibly exist given that these principles hold true. So do you have an idea? Right. So do you have an idea for the different outcomes of this research project?
Yeah, sure. This would be like a bit cheating, but like there are 4 possible outcomes, but the good part is that any of the 4, if the task is completed, would be like very exciting to me. The first is that only quantum and classical systems exist, so that there can be only 2 types of information, which is either the information is classical or either the information is quantum. This would be great because like all the theory, like if any physicist in the future proposes, oh, but there could be a new type of system that is like does not adhere completely to quantum mechanics, but is also not classical in information theoretic terms. then you can show them this and say, no, like you cannot propose that because we know that, or we expect that this is not the case because we expect these principles to hold true forever. Second case is that the quantum scenario is the extreme, like in the sense like it's the weirdest you can get, some sort of, but then you can have different theories or different types of information between classical information and quantum information. So there is a huge realm, maybe like this is a possibility, one of the four, this is the second, where you could have a different type of information in between classical and quantum. Why this would be nice? Because like nowadays, for example, a lot of people is focusing on developing quantum information or quantum computation or quantum communication because it has so many advantages versus classical computation communication. But if we are able to find this in-between regime, maybe a lot of people in business or like us as a society, we're saying, okay, maybe it's not necessary to go full quantum. Maybe the exact applications or capabilities that we want, it's in one of those in-between theories, and there's no need to go fully in the quantum case, although I would guess that, I don't know, I would guess that it's not, like, it's also preferable to have quantum. But I don't know, like you will have new theories to explore and then to check if what physical systems adhere to them and all this sort of stuff. So it opens possibilities. The third is that in between classical and quantum, there's nothing, but you have things beyond quantum. That this could be useful because it will inspire the search of dynamical laws of the future. Because right now, for our experimental capabilities, we expect to be quantum, that quantum mechanics is general, but they also thought that like in the end of the 19th century. So it would be interesting because also it could be explored if some of the unsolved mysteries of today, like especially on the overlap of quantum mechanics and general relativity, they are not compatible because we are looking at the wrong place. We are looking inside quantum theory and we need to go beyond. Or it could be that the cases 2 and 3 combined, and this would be even better because you would have both things. That you have more richness, like in the experimental side, like in the business side of information theories, but also you will have it for theoretical physicists who are trying to look between quantum and general relativity. But if the classification is successful, and I hope it will be, what I expect is that the framework itself, if it gives like one of those scenarios where you have other theories, I think that the framework itself will hint you or will tell you what type of dynamical law you will have to have in order to have that that information type or that type of information. So the framework itself will tell you where to look or what features you will have to look. You would say, okay, I want, like you're saying that this exists and there is this weird type of information where you can do all this sort of stuff, but where I go find that, what I have to look for. But I believe that if the classification is successful, the framework itself would tell you what you have to look for and would inspire the search for these other theories.
So you'll have to formalize constructor theory a lot more to solve this problem and create this classification, correct?
Yeah.
So let's talk a little bit about that. So as far as I know now, we have attributes and tasks as being integral concepts in constructor theory.
Yes.
So if you could tell us what these concepts are and why is their current formulation not developed enough for you to succeed now in your research program?
Sure. Basically, attributes are the properties that can be changed under operations. So physical systems have properties, and we call attributes the type of properties that can be changed, for example, or that can yield information about the system. For example, if I have an apple, one of the properties, one of the attributes would be being red. This is an attribute, and usually physics does not talk in those terms. Like if I have an apple, it would talk about the coordinates of all the constituent particles of the apple, but it would not talk about the attribute of being red, which in itself, it can transfer information in the sense of, if I show you a green apple or a red apple, it doesn't matter the size or like the position of all the particles, or if or anything. Like we can transfer information only on the basis of if the apple is red or not. So this is an attribute, is a property of the system, broadly speaking. The crucial part of constructor theory are tasks. Tasks are the transformations that you perform that change the attributes of your system, basically. This is what tasks are. They are assignments between attributes. And the current formulation of of constructor theory, what it does is, like, in order to not assume and to preserve the generality of the framework of a system, what it does is just says that about tasks. They do not put any other mathematical property or constraint into what a task is, rather than an attribute is this object, this element, and a task is just an assignment between elements, and that's it. This is great to preserve generality, and it has produced a lot of results using these concepts. But what I'm trying to do in order to provide this classification is just to, I'll do it in two fronts, basically. The first is to study these networks, the network of tasks, because at the end, what defines a system is what operations you can perform to it. So what you want to study is the network that you have of possible tasks, and seeing if the shape of this network is different, then trying to classify the types of information that system can encapsulate or not. This is the first thing. And the other thing that I'm looking forward to do is using this principle of locality, then I can have more of a mathematical structure in terms of this assignment that are tasks. So I will not only be able to say A goes to B, I will be able to say A conforms to this specific mathematical formulation, not very specific, but this sort of preserving generality, but at the same time giving more richness in structure. So A has to be of this form, and B has to be of this form. So the task has to preserve this form. So therefore, then I would have a structure. Like, I know I'm saying the word structure too much, but I will have these properties of the task that can be exploited and can be classified depending on which structure do you have. And as I said, like looking at the global network of tasks, depending on which shape, you would have one type of information or the other.
And have you found any promising mathematical structures, as you say, that might be the formal language of constructor theory?
Yes. So, like, the answer to my last question, it's not like a guess, it's before jumping directly to research, you do like a preliminary survey of what you will be able to do or not. So yes, as I divided in the other question, I have found like two promising mathematical concepts that can be used in formalizing constructor theory. The first is using this notion of studying the network of tasks by itself, and this would be using graph theory and network theory, and trying to classify different graphs to then lay different information properties. But not only that, using the second approach, where I'm posing structure in the attributes and in the tasks, the form to do that, I believe, is to study the so-called group or yeah. Now, can you hear me?
I can hear you. I think you dropped out for a couple seconds.
Sorry.
Last thing I heard you say was group.
All right. So yeah, the posing this structure in the attributes and in the tasks is done basically through group theory. So what we want to study is graph theory with the global network of the tasks, but not only that, we want to study it in terms of what group theory can tell us, like that it has to do of how the different operations, how the different tasks of your system can combine. What are the laws of combination between different tasks?
Okay, great. Yeah, people are going to be excited about that. I see a lot of people looking into what's the math of constructor theory. So that's nice. Thank you for telling us.
Oh, that's right.
So are there other branches of constructor theory to which you expect your mathematical formalism to apply? And if so, what other open problems might it solve?
I believe yes, because even though I'm focusing on the information theoretic part of constructor theory, I believe that formalism would be general enough for all constructor theory to be put in those terms. What I would also like to see, if there is like once the framework is completely developed, if there is a more handy way to use notions as tasks or that are not this super abstract, rather than you can have some sort of, I will get a bit technical here, isomorphism, in the sense of you can have a one-to-one assignment between what a task is and some sort of more numerical representation. So you can perform calculations or this sort of stuff. So yeah, I believe that I expect the formalism will be general enough that it will apply to other parts of constructor theory. And not only that, like having this separation using the Einstein's principle of locality gives you a lot of tools for the researchers to, like having a mathematical formulation or having a structure when you are dealing with a problem. It gives you a stronghold where to start with. Like you can start writing, okay, this is the definition of the stuff I want to explore. Now let's find patterns, or let's try to capture mathematically what I want to say about these objects, and try to translate it in some sort of an equation or some mathematical relation between those objects that now I have a description for. So I think that two of the open problems that could be solved using this sort of intuition, and that formalism would help to tackle, would be first in the context of constructor theory of thermodynamics, in the sense of seeing if from reversible dynamics, if you can have an irreversible task. This is the first thing. So the framework would be important because, like, if I have a precise notion of what an attribute is, then I can have a precise notion of what reversible dynamics is. And if I have a precise notion of what mathematical entity represents a task, then I can pose the question of what it means the task for be completely irreversible. So only by having the definition, then you can more or less hint at which would be the relation that you want to answer if the question, if this is possible or not. And another area which I think that it could be great is in the notion of constructor theory of life, of the notion of what are the features of the system in order to be self-reproducing. If you have this group notion and you are able to somehow, I don't know, I'm just guessing, if you're able to say a system will have the ability to self-reproduce if these group identities are satisfied, then you can pose that as a mathematical equation for which groups, like which group has to be represented in order for this to happen. Then you can try to solve that equation, and then you can do two things. First, see if the current systems that you know that are self-reproducing are can be described by one of the solutions. And second, what you can do is, if there are more solutions, you can try to implement them in the real world and seeing, okay, since I know exactly what it has to do in terms of group theory, this represents group theory in the real world. Therefore, I know that if I do these precise operations, I will grant this system the ability to self-reproduce.
Got it. Those are both very exciting developments. I look forward to watching them. Well, Nicetu, it sounds like you're working on a very ambitious research project. I wish you the best of luck, and I look forward to speaking with you again sometime.
Yeah, thank you.
Thank you.
Very much. Thank you.